Tony Stark has contacted a team of ME 2110 students to help him with a mission to explore the moon called One Giant Leap. He has entrusted them with his artificial intelligence on this mission called Jarvis Mark II to perform set specific tasks upon their arrival. Upon landing on the moon, Jarvis Mark II is placed upon a track with a starting zone of 30 inches by 30 inches, with 4 different sections divided by color. Limitations are that Jarvis Mark II must not exceed these given dimensions: 12 inches in length by 24 inches in width and 18 inches in height. The use of energy from controllers, 5 provided mousetraps, and 5 provided rubber bands, along with gravity and a budget of $100. The final design must be fully automated and powered by the track using a mechatronics kit and MyRio program. Jarvis Mark II is to perform 5 specific tasks and consistently score the highest number of points, totaling 200 per trial within a 40-second time period. The 5 tasks are deployment or triggering the robot, rock clearing the Sea of Tranquility without touching the lunar module, sensor decoy placement into each opponent zone on the lunar ridge, which spins at a speed of 5 to 7 revolutions per minute, and then flag deployment and egress. Engineering design tools were utilized to create different solutions for each problem, such as a house of quality, specification sheet, function tree, and morphological chart. Engineering design principles were used, such as a house of quality shown here. As per Tony Stark's requirements of the team, Jarvis Mark II must be fast operating, accurate, consistent, safe, durable, low cost, and efficient on his moon exploration mission. Through studies of the relationships and weighted importance of Tony Stark's demands, this reveals that the number of moving parts at 17% weighted relevance and the operation time at 16% weighted relevance were the most important engineering design specifications. However, there is a trade-off between the cost of production and durability of the machine. Durable, cost-effective materials must be selected. Critical specifications within the specification sheet point to energy consumption of less than 100 watts, an operation time of less than 5 minutes due to the automation of events, and minimal reset time of less than 10 seconds per trial. Function tree, as shown, breaks down the 5 main tasks into essential subtasks as a different problem understanding approach to engineering design. Select challenging subfunctions where clearing the rocks from the Sea of Tranquility, deploying the sensor decoys into each of the opponent zones upon the lunar ridge, and preventing more than one sensor decoy from being released at a time.
The morphological chart allowed us to recognize different types of mechanisms possible for our machine, giving us a guideline as to which mechanism to go with. In deciding the design of the rock clearing arm, we chose not to go with the mousetrap because of the amount of time it took to reset each time, and due to the fact that it would require a more complex design of the rock clearing arm. As for the flag arm, motor-powered flag arm was chosen over mousetrap-powered flag arm because the motor-powered flag arm had an advantage in the egress process of the flag arm than the mousetrap.
After going through the house of quality, specification sheet, function tree, and morphological chart, the following designs were selected to accomplish each of the tasks. For the trigger mechanism, a custom 3D printed part, an actuator, and the gravitational potential were used. The trigger itself is attached to the column with a single screw. A loop is connected to the body of the machine, which is tied around the collar of the trigger. The actuator is placed beneath the triangular part of the trigger so that when the valve opens, the actuator hits the triangle body. For the lock clearing, a rotating arm has been selected for the final design. The arm is directly attached to the motor via a coupler. The round shape of the arm is specialized to push out the locks from the Sea of Tranquility while avoiding the lunar module from displacing. The zip ties on the tip of the arm help to push out locks to a further distance. For deploying sensor decoys, the solenoid gate has been chosen. The solenoid acts as a door that opens and closes for each of the decoys to come out at the right time. The solenoid has been slightly modified with a spring and a string. The spring compresses when the solenoid is activated and decompresses when it's turned off.
Let's talk about the concept alternatives that went into this overall design. So for task 1, launching the device, we had two main mechanisms, as you can see here. You can push the rail slides via an actuator so that you're actually applying a force to the rails, or you can instead tilt the rails at an angle so that simply releasing the rails will trigger the device. For task 2, clearing the rocks, there again were two main possibilities. We could either push the rocks out of the way and use a mousetrap to send the third lunar rock out of the Sea of Tranquility, or we could use a rotating arm that would sweep the rocks away, as was done in the final design. For task 3, deploying sensor decoys, there were three different concept alternatives. One was a candy machine design, which involved a cylindrical device with these walls that would spin and move the sensor decoys towards a slot, where they would exit the device at the appropriate zone on the lunar ridge. You can see the design concept here. Then we also had a 4-lever cart idea, where the cart is primed by gravity and holds 3 of the sensor decoys. Upon hitting a height adapter on the lunar ridge, indicating the current zone, the appropriate sensor decoy would be released. The third and final idea is the solenoid gate idea, and this is ultimately what we went with. A solenoid with a spring inside would act as a gate for a gravity-primed cart. When it is turned on, the gate will retract, allowing sensor decoys to pass through. When the solenoid is turned off, the spring will cause the gate to close again. For tasks 4 and 5, the two main concepts both involved a hinged flag arm. One of the ideas was mechanical, using a mousetrap to spring the flag arm onto the lunar ridge and egressing via a winding string and motor. In the second idea, a motor would be used to turn the arm one way for planting and the other for egressing. So how did we actually decide between all these different designs? Well, first we determined a couple of important criteria taken from our specification list in the House of Quality to evaluate each of them using an evaluation matrix. For task 1, as you can see, they decided to use primed rail slides that only need to be released rather than pushed. This was mechanically simpler, contributing to the ease of manufacture criterion and made it a better choice. For task 2, the rotating arm ended up winning due to the greatly reduced operation time, since the mousetrap did not need to be set up before each trial run. For task 3, the solenoid gate idea won by a slim margin against the candy machine idea. This was largely due to its ease of manufacture, its improved safety, and its durability. For tasks 4 and 5, ultimately, the motor arm was chosen over the mousetrap idea due to its simplicity, its ease of manufacture, and its improved accuracy. These are the main highlights of each idea that explain why they were more beneficial than the alternatives. Next, we'll talk about the competition results.
In the first round, Jarvis Mark II was able to score the maximum 200 points. For the second and fourth round, the flag arm became stuck to the top of the lunar ridge due to tolerance of the 3D printed flag holder, not accounting for glue, and strong magnet of the flag base, which put Jarvis Mark II in 10th place overall at the end of the competition. The team surmised that testing of different flags was necessary to avoid this situation, as different flags had different base diameter due to different amount of glue.